This is a very useful question, so I hope you are watching this video because it connects two very difficult part of this chapter, which is this sound diagram where you see all these dots representing particles. We have to connect this to graphs, to a graph for sound wave. So there is some techniques here that you need to know how to apply, to use. So I've talked about this in a previous video also in the MCQ, and I'll repeat the same thing here also. So part A, describe the type of wave, not difficult. Longitudinal wave, describe it in terms of the particles' motion. They are oscillating or vibrating parallel to how the wave is moving. For part B, the region P4, P5, P6, they are all very close to each other. If you can see the particles here, they are all close to each other. So P5 is at the compression point. For part C, let's start with the wavelength. That's the easier one. So, like I've always said, identify the compression first. P5 is compression. P13 is a compression, and then identify rarefaction, which is either you find particles where the neighboring particles are very far apart from it, or you just find two compressions, find the midpoint. So the wavelength is always from one compression to the neighboring compression, or from one rarefaction to the neighboring rarefaction. So that's how you can get the wavelengths. Now, for part D, before part D, for C part 2, C part 1, the amplitude. So I've talked about this before also. Look at the rest position and look at how each of these particles have been displaced. Notice that for P3 at this point in time, it is displaced the furthest away. So therefore this becomes the maximum displacement, which is the amplitude of the wave. Now for part D, read carefully the question. It says that between these two figures, each particle has already executed or taken 1/4, or has already moved 1/4 of a complete cycle. So between these two diagrams, the time span is 0.2 seconds. Look at this time, 0 seconds, 0.2 seconds. So this means that 1/4 of a cycle is 0.2 seconds. So the answer to part D is actually quite simple if you understand the question. Just use 0.2 seconds multiplied by 4. That's the time taken for one complete cycle. Okay, so that's for part D. Now E is the tough one, but we'll run through this together. So first up, this is the answer, and I will show you how I get this answer. There are certain points, certain plots that I will start plotting before I draw in a sine graph, because we all know that for displacement time graph or displacement distance graph is always a sine graph, sine or cosine graph. So, but the challenge is how does, where do you start the graph, and whether do you start going downwards or do you start going upwards. So I'll show you how I arrive at this answer. First up, I noted that this must be the first coordinate at 0 lah. So there's 0. And the second coordinate that I'll do is here. Look at all these coordinates. 0.8 seconds, 1.6 seconds, 2.4 seconds. How do I know this? Because one cycle, the period is 0.8 seconds. So that means at 0.8 seconds, 1.6, 2.4, 3.2, at this point, right, the particles there must be at rest position. So it's one complete cycle. So I plotted in these few coordinates first. Then next up, look at this. Alright, so in between, I'll just put in 0.4 seconds, 1.2. So in between, the particle must be at the rest position. I mean, if we started off with a rarefaction, this one must be a rarefaction, and in the middle must be a compression. Either way, compression, rarefaction, compression, rarefaction. So at all these compression, rarefaction points, the displacement of the particle must be 0. So I have put in all the easy coordinates. Then next up, how do I know that the graph goes downwards at first? I look at this. So I noted that in figure 5.3, particle P1 previously at time 0 was here, but at 0.2 seconds, particle P1 is found on the left. So particle P1 has displaced towards the left, and displacement towards the left is negative as instructed. So that means for this particle P1, when we start timing, the particle move negatively, move towards the left. That's why I know that the graph over here at time 0 and at time 0.2, right, it moves towards the negative displacement. So it moves downwards. And at 0.2 seconds, it's found at the amplitude value. Amplitude value we found just now is 1 cm. So over here. Okay, so basically what I'm doing here is trying to draw a sine graph or negative sine graph over here. And now that I know that the graph must start going negative, it's basically trying to fit a sine graph inside. And naturally your midpoint here at 0.2 seconds will be the amplitude value. Alright, so this is how the tricks that I use to draw this sine graph. This can get a bit tricky, so replay the video and also seek help from your teacher if you need.